So today, we're very happy to have Professor Zoltan Haiman visiting us. And Zoltan is going to give the CITA seminar talk today. Professor Zoltan Haiman received his Physics Bachelor of Science degree from MIT, and then he attended graduate school in Cambridge, UK, and at Harvard University, where he received a PhD in astronomy in 1998. Before joining the Columbia Department of Astronomy, he was a Hubble Fellow at Princeton and a postdoc in the theory group at Fermilab. So Professor Zoltan Haiman has won numerous awards, including he was chosen as one of the Popular Science magazine's Brilliant 10 Young Scientists in 2002, and received the New York Academy of Sciences Blavatnik Award in 2010, and the Simons Fellowship in Theoretical Physics in 2013. Professor Haiman's research has explored broad topics in theoretical astrophysics and cosmology, including the formation of the first stars, the emergence of massive black holes, and the nature of dark energy and dark matter, as well as astrophysical sources of gravitational waves. So today, Zoltan is going to tell us about the gravitational and electromagnetic signatures of the black hole mergers. So now I will hand this to Zoltan, please.
Yeah, so let me share a screen. Thanks. Share the screen.
Okay.
Can you see the screen? Yeah, can you see the screen?
Yes, I can see it quite well.
Yeah, so thanks. Yeah, thanks for the invitation. I have to say, I have to start by saying I'm really sad not to be there in person. I was looking forward to visiting. So instead I put my background. This is the closest I got to Canada in the last few months in the Adirondacks. I hope to visit in person at some point in the not so distant future. So this talk, I mostly want to talk about supermassive black hole binaries, which merge in galactic nuclei, and their behavior and electromagnetic emission properties and their dynamics. And a lot of this work was actually done by students at Columbia, listed here, and my collaborators at NYU, who were students of Andrew McFadden. And I need to start by something that I've been announcing in my seminars, because I read an interesting book. And I want to start by asking how many people actually know where the word black hole, who coined the word black hole, since I'm going to talk about black holes. So I don't know, you could raise your hand, I suppose, or shout the answer if you know.
It's John Wheeler at Tom's Restaurant, right?
So yeah, so
Fred Hoyle.
No, so yeah, the most people know the answer, that John Wheeler, who was a professor in Princeton, coined this term black hole. But I'm sharing this story because I read his autobiography, which was published in actually quite a long time ago. And here he says in his autobiography that in the fall of 1967, Vittorio Canuto, the head of NASA's Goddard Institute for Space Studies in 2880 Broadway, New York, invited me to a conference where he talked about pulsars. And he, in his talk, said we should consider the possibility that at the center of a pulsar is a gravitationally completely collapsed object. And he also said one cannot keep saying that this long term over and over, so you need a shorter phrase. And then how about black hole, asked someone in the audience. And he goes on to say how he had searched for this term for many months, mulling it over in bed, in my bathtub, etc. Suddenly the name seemed right. So apparently, according to Wheeler, an anonymous person during his seminar suggested this term. So I'm just, I have to share this because if you were with me here in my office, and if you've been at Columbia, this is the view I have from my office. You walk out of campus, you go to Broadway, and this is 2880 Broadway over here, which is Stone's restaurant. And then up these windows here are the windows where the NASA Goddard Institute for Space Studies is located. So somebody in one of these rooms apparently is responsible for this term, at least according to Wheeler. So let me move on to more scientific topics. So in this talk, I actually wanted to go through an introduction why mergers of supermassive black holes are generally believed to happen and why you should care about it. And most of the talk will be theory part, which presents simulations of hydrodynamics around the binary, and I draw some conclusions from that. And then an observational part where I will argue we have some candidate, such very compact counterparts based on their electromagnetic signatures. And I most likely won't get to part 4. We'll see how these Zoom talks go in speed. But a lot of the conclusions from studying black hole binaries in gas disk also carry over to compact stellar mass objects and related to recent LIGO observations, which if we get to, I'll say a few things. Let me start with a motivation, which is actually quite simple. So we all know that that most galaxies, most major galaxies contain a supermassive black hole whose mass is in the range of millions to billions of solar masses and correlates with the mass of the host. Roughly 0.1% of the host spherical component of the host is the black hole mass. And in fact, we also know that black holes were formed very early on. So this is the luminosity function of quasars going from redshift 4 all the way to redshift 6. This is just the tip of the iceberg. So these are 10 to the 8, 9 solar mass black holes at redshift of 6, but they were present and presumably arose from smaller seeds. And a decent explanation is that these seeds were placed in the universe very early on and then just evolved and accreted and merged later. And that explains the evolution of the quasar's luminosity function, which we wrote a whole review paper about. But for this story, it's important to just, the important point is that there are black holes in galaxies early on, and then the galaxies merge. And of course, we know that galaxies, how many times galaxies with certain masses would merge is just derivable from hierarchical structure formation, from theory, but also from observations. We know that and can build models where a typical galaxy undergoes several major mergers during its lifetime. So, and there are of course examples on the sky, so you don't have to believe the theory to know that galaxies merge. And the last bullet is that most galaxies have gas in their nuclei. So one reason this correlation is important is because we can say that typical black holes, which are in nuclei of galaxies and have masses of several tens of millions of solar masses or less, they're typically in disk galaxies, which are very gas rich. Now, the biggest black holes above these tens of millions of solar masses are typically in so-called dry elliptical galaxies, but even those ellipticals contain some gas. In fact, I just like to show, I mean, this is a picture of a disk galaxy. This is a picture of an elliptical where the largest, most massive black holes sit. This is M87, and we had the Event Horizon Telescope observation. So even the M87 black hole is accreting. There's some gas around it. And we don't need much gas. In order to influence these black holes, we need an amount of gas roughly comparable to the mass of the black hole. So just 0.1% of the galaxy mass is it's in gas. It's important potentially dynamically. And then the last bullet is during a merger, we also roughly understand what happens, at least until we get to the very smallest scales, is that during a merger of two galaxies, the massive black holes suffer dynamical friction on the stars and the dark matter, and they sink to the central few kiloparsec region. And the gas, which is in the galaxies originally, also flows to the center because its angular momentum is removed by a process that's been actually well understood for 2-3 decades. There's a misalignment between bar structures which form in the gas versus the dissipation of a stellar component, which are misaligned and provide torques and channel the gas to the center. And this gas also cools and loses its support in vertical direction and forms a disk. So all of this motivation should sound, I think, decently reasonable, and it implies that there's a common outcome of these merger processes and galaxy formation, which is pairs of massive black holes appear in galactic nuclei surrounded by a gas disk. Now, can we see these observationally? And the answer is only down to certain separation because they're hard to resolve. So the poster child is this X-ray image of this galaxy NGC 6240, where we have two active nuclei. So clearly there are two black holes, clearly there's gas, and it's on kilopar. The separated projected separation is kiloparsec. And they're still quite far apart. In terms of even more compact, they get very hard to see. So there are several dual or offset AGN in optical. They tend to be more widely separated. And the winner is, in terms of closest separation, is a radio galaxy, which has two active nuclei with a projected separation of 7.3 parsec. And just for reference, if you take the scaling relations, this is the famous M sigma relation, and ask what is the sphere of influence of a black hole, so GM over sigma, where M is the black hole mass for the central velocity dispersion sigma, then for a 10⁸ solar mass black hole in its host galaxy, which has a 200 kilometers per second dispersion, it's 10 parsec. So if you want a genuinely gravitationally bound binary, they would be more compact. The separation would be parsecs, less than 10 parsec. And so maybe this AGN could fit that bill, but marginally, but in general, we don't have any example of an actually spatially resolved, gravitationally bound compact nuclear binary. Now we're interested in the fate of these binaries, whether they can actually get to close separations and eventually merge. So another separation to keep in mind is the following. So if I take two black holes, they emit gravitational waves and spiral in, and then they can merge, but it takes time. So if you take two black holes with 10⁶ solar masses, and you ask how far apart they can be so that they merge within 10 gigayears, it's a milliparsec. Or if you take two 10⁻⁻ solar mass black holes and you want them to merge in the age of the universe, it has to be 1 parsec. So these separations are quite small, which means if you want to get to the point that they're observing gravitational waves, you have to somehow cross this barrier and go to sub-parsec regime with some process which can then be taken over by gravitational waves. So you have to have another process that delivers these binaries to be very compact. And those could be stars in galactic nuclei, scattering on stars, or I'll argue in this talk, gas can also do the job of crossing this bottleneck, where large-scale galaxy merger torques and dynamical friction can deliver the black holes to this point where you want them to be for gravitational waves to actually finish the merger. So gravitational waves, just to emphasize that mostly the black holes I'm interested in this talk are these supermassive or massive binary black holes. So the most massive ones, 8 to 10 solar masses, are targeted by pulsar timing arrays. The lower mass supermassive black holes, up down to 10 to the 4 solar mass or so, are targeted by LISA. And then, of course, LIGO has already discovered black hole mergers in the range of 10 to 100 solar masses. And the distinction, and the reason I'm focused on the more massive ones, is that the general conventional wisdom is that most of these mergers might happen in vacuum, and most of these mergers will be in galactic nuclei. There's plenty of plasma, and so this is a sort of better motivated problem for the more massive black holes, but I actually don't think that's necessarily 100% true, which is why if I ever get to it in this talk, I'll discuss the possibility that LIGO sources also have gas around them, and then what that implies and how that could be arranged that they have gas. So the scientific motivation, what you could do if you had gas around the binaries which emit radiation, and you could measure that jointly together with the gravitational wave emission, would be especially very interesting. And I would say there are 3 types of motivations or extra things you can get out of this dual observation, which is nowadays called multi-messenger astrophysics. So the first kind of thing you can do is most relevant for astronomers and astrophysicists. First, you can study accretion physics in unprecedented ways, because we know the light curves and spectra of black hole binaries with known parameters, known masses, and known spins and known orbits. Also, I'll mention in my talk, we can study accretion physics in the sense that if there's gas around the binary, it can actually distort the gravitational waves, and those distortions depend on the gas disk properties. So LISA, you could think of it as a way to study accretion disks by looking for very subtle distortions on the gravitational waves. We'll of course also learn the connection between quasars and galaxies, because if we have the counterparts, we know which LIGO merger happened in which galaxy and can follow this over time. That's a long-standing problem now in astronomy. LISA can peer out to the dark ages. So if you see the merging black holes and you see the ones that shine in X-rays, you can compare the buildup of early black holes by the importance of mergers versus accretion. Other topics you can explore better with this multi-messenger detections are there intermediate mass black holes, which you can see in mergers as well as photons. And again, my other subject is the formation, the channel, and the fate of stellar mass black hole binaries can be discovered by combining LIGO types of observations with electromagnetic counterparts. We of course still don't know where the LIGO binaries came from, but if we see photons from some of the black hole mergers, that might become clearer. Then more fundamental physics and cosmology. There's of course the most prominent use of multi-messenger sources is from combination of gravitational waves to measure the distance to a in-spiraling binary that's actually chirping over. So it's in spiral, its frequency evolution is measured in the gravitational wave data. It gives you distance. Spectrum would give you redshift, and you can plot the Hubble diagram. This actually I was less excited about, maybe slightly originally, because we have other ways to measure the distance, luminosity distance redshift relation from supernovae and other things. But in light of the current Hubble tension, I think this is actually quite interesting, because we have a single method that probes a very large redshift range with a single type of systematics where we can study the Hubble diagram. And then maybe even more interesting is actually a topic that Kristen Menu, who I think is not here, has worked on a while back, which is you can also compare the electromagnetic Hubble diagram with the gravitational wave Hubble diagrams, and if photons and gravitons behave differently, then they might not agree. And then you can discover modifications from general relativity, including things like extra dimensions where gravity is weakened on large distance scales, or massive graviton theories where gravitons propagate more slowly than light, so they arrive with a delay. And in fact, from this simple equation, if you measure the frequency of the gravitational waves and you measure the gamma from the time delay between photons and gravitons, then you can infer the mass of the graviton. And if that's frequency dependent, then you can probe Lorentz violating theories, for example. All of these are things which you can only do if you have electromagnetic radiation and gravitons together from the same source. Lastly, of course, EM counterparts are potentially very useful to excavate more detections from the gravitational wave data stream, marginal sources whose confidence might be boosted by seeing a concurrent electromagnetic source. So this would be great. And of course, the question is there actually electromagnetic radiation from binaries? So I move to the next part of my talk, which is a discussion of, in general, what happens to a binary with a disk around it. And I have an extremely naive way of thinking about this problem, which is we know how quasars operate. There's a black hole, there's a geometrically thin, optically thick accretion disk, outskirts of which might be gravitationally unstable. The mass of the disk in the inner regions is very small compared to the black hole. So if we assume that somehow the black hole is already navigated and the pair is sitting in this part of the disk, then we can simply say we just want to know what happens to a usual accretion disk if you have 2 point masses in the middle rather than 1 point mass. And so that's a very simple setup, which we'll do in a second, but I just want to reiterate that this calculation is important because we want to ask, is there gas near the black holes? In terms of electromagnetic signatures, we want to just know, does gas actually accrete and come within few Schwarzschild radii of the black holes? And how does this accretion take place? This is clearly important because if you want a bright source, we want accretion. And if you want observational signatures, you want to know what is the spectrum and the variability properties. The second thing we can do with this kind of simple circumbinary disk studies is ask, well, does the disk affect the orbit of the binary black hole and vice versa? So do the disk torques help or the binaries to merge, as I alluded to in the beginning, or maybe it's an obstacle? And in particular, is the time scale right in the sense that can gas disk actually promote merger within a Hubble time? So this also is important for observations because if gas disk merges black holes very quickly, you see fewer binaries on the sky. If the merger takes longer, you see more binaries on the sky. So observed populations are affected by this. And the last thing you want to do is ask, in this kind of hydrodynamic setup, can we produce the electromagnetic emission during the last phases when the binary is merging? And can the waveforms, the gravitational waveforms, be modified by the presence of the gas? Okay, and of course, it's also just an exceptionally well-posed physics problem because we just want a near Keplerian thin disk and its hydrodynamics with 2 point masses. So it's almost like a textbook problem. So the cartoon picture, which was quite often invoked even 10, 15 years ago, is that the basic difference is that if you have 2 point masses instead of 1, there are no stable orbits in this region, which are roughly twice the separation of the binary. There are, of course, stable orbits within the heel region of each black hole, but around them, there's no stable orbits. So the cartoon picture is that there can't be stably accreting gas in here. So there's maybe a large punctured disk with a large cavity, which might build up a rim, a dense rim. And this would be not so good because if the gas cannot get to the black holes, we can't expect electromagnetic signatures. So the simulation version of this is something we've been working on for now quite a long time in collaboration again with the NYU group of Andrew McFadden. And we've been using a code called Disco. It's a 2D moving mesh. It's a moving mesh grid code. And we've used it so far mostly in 2D. There's also another moving mesh code called Mara. But most of the results I present are from this code Disco, which was mostly written by Paul Duffel while he was still at NYU. And it's public, so you can actually download and run this kind of simulations yourself with this code. It's very efficient because it's moving mesh. And this is a pure hydro in 2D. We do have pseudo-Newtonian beta Paczynski potentials for the results which I will present, which are relate to close to the merger. Otherwise, it's just Newtonian hydrodynamics. When the black holes are more than tens of Schwarzschild radii apart, that's legitimate. The viscosity is simply an alpha prescription. The disk cools backbody radiation from the surface, and it's heated by viscosity and shocks. The black holes are on the grid, and they can accrete. So they're directly followed, and they're accrete by a sync prescription. And one advantage of doing 2D simulations is that you can make the disk very large, 100 times the binary separation, so that outer boundary conditions are safely not spoiling the calculation. And the other advantage of doing 2D is that you can run many orbits. We can typically run up to 10,000 binary orbits. That's important because then the inner disk actually reaches steady state, meaning you run the simulation for longer than the viscous time of the gas near the binary. So you can establish a steady pattern. And the most important parameters in this extremely simplified numerical setup is just the binary mass ratio, Q, which is less than 1. It's the smaller black hole divided by the secondary divided by the primary, the eccentricity of the binary, the temperature of the disk, or the scale height h over r, and actually the most interesting one is probably the mass ratio. So let me just present the result by looking at one particular movie, which is just for an equal mass binary. So this shows the surface density of a binary, which is revolving around this way, but the movie is in the co-rotating frame, so the black holes appear stationary. And well, you can admire the movie. And see very conspicuous features here. For example, there's this large cavity. There's this dense lump which forms at the edge of the cavity. The cavity is actually not very circular. And there are streams of gas which get near the black holes, and they feed these things which are called mini disks. So these are the main features. The central cavity, which is kind of expected, is indeed present and results in this region having density which is 100 times or so less than the density further out here. Another important feature for observations is that this cavity is lopsided and develops this lump at the edge of the cavity at a particular azimuthal angle, which can modulate the accretion. And this lump, we actually understood it forms due to a nonlinear instability, in the sense that these streams which get, maybe I go back to the movie. It's a little hard to see, but there are streams which are moving outward and hit the edge of the cavity. So stuff is peeled off from the wall of this cavity, tries to accrete on the black holes, but a large fraction of it is flung back out in a slingshot and hits the cavity wall. and that causes these compressions. And the way this works out is that it's a runaway. If there's some small loss of symmetry, it tends to develop this lump, because it keeps enhancing one stream at the cost of the other. And the other conspicuous feature here is that there are streams of gas entering the cavity due to shocks, which penetrate the tidal truncation regions of each individual black holes and form these mini disks. And the accretion basically happens through these shocks and not particularly through viscosity. That will be important. If I get to my end of my talk, this is actually important for seeing the LISA counterparts. And then the mini disks, which you can see around the individual black holes, they're fueled by these streams, and the net accretion rate. Well, first of all, this you can even see in this picture that sometimes these disks are present, sometimes they're not. They're periodically modulated, but the net accretion rate is actually not diminished compared to a single black hole, which is probably the single most important conclusion from this kind of simulation, that this binary propeller is very efficient in creating this cavity and not allowing gas to build up here, but it's completely inefficient in preventing gas from accreting on the black holes. The gas still comes in. It just comes in streams as opposed to quasi-Keplerian in spiral. And the important point is, why does this accretion happen at all? And the idea here is that this is due to shocks. So this is a snapshot from this kind of simulation showing the density, projected surface density. Red is dense, blue is less dense. This is one snapshot, and it shows the velocity field, and you can see how gas gets shocked into these narrow streams. So the interesting comparison to this in terms of physical explanation is something you can easily do yourself, is solve the restricted three-body problem. So here I put two black holes near the origin, and I put a bunch of massless test particles on Keplerian orbits in this annulus. And you can then follow the orbits analytically, of course, of each of, well, almost analytically, of these particles. This is again in co-rotating frame after 1/4, 1/2, and 3/4 orbit of the binary. And you see what happens is basically in this restricted three-body approximation, all the particles that there are two quadrants in which particles lose angular momentum and form these fingers. And the other two quadrants, gas gains some angular momentum and moves further out. Now, of course, these trajectories cross each other, and you cannot interpret this afterwards, these simple orbital calculations. But you see that this is just fundamentally what gravity tries to do to this disk: pull in these streamers and push gas away in the other two quadrants. And it does look very similar what you get in simulations. Instead of orbit crossings, you get shocks at these locations, and gas loses its angular momentum in the shocks, and some of it ends up accreting onto the black holes. Was there a question, or that was just a cough? Okay, no question. The most important thing is the accretion rate. So here I show the accretion rate in these simulations for two cases, which are typical for binaries which are near equal mass on the right and more unequal mass on the left. And these are the kind of mass ratios you actually expect in galactic nuclei between 0.01 and 1, because very unequal mass galaxies don't necessarily end up having enough dynamical friction to pair up their black holes. So in this interesting range, it turns out the accretion has three regimes. One is if the mass ratio is below 0.05, so more unequal than 1 to 20. Then I'm not showing that because it's very boring. The accretion tends to be just very steady and essentially matching the accretion rate you would have in a single black hole disk. if you make the mass ratio larger, up to about 0.3, then this is what you find. These are m dot over m dot 0. So m dot 0 is from a reference simulation where we have one black hole instead of two. And the green is the accretion rate on the lower mass black hole, and the blue is the accretion rate on the primary, the larger mass black hole. And you can see two things. First of all, the secondary black hole completely out accretes the primary, and that's because it's displaced from the center of mass more, so it's closer to this cavity wall. So the secondary lower mass black hole kind of gets first pass at all the stuff that's coming in. And so it's driving the system to more equal mass. And also the accretion rate is not below 1. So in fact, it's even slightly larger. And so therefore, this secondary black hole that's dominating the accretion should be just as bright as a regular quasar if the m dot 0 is matching that of a quasar. And the periodicity is completely obvious on this plot and tracks the orbital period. So this is the periodogram or Fourier transform of these light curves. If you go to the more massive ones, which is the simulation I showed in the movie, this is for 0.7, then the two black holes behave similarly. So they're similar masses. And now, again, the accretion rate in terms of the single black hole accretion rate is not suppressed. So each black hole accretes a little more than half it would have accreted of a single black hole. So the sum total, again, is slightly even exceeding the single black hole rate. So these are two bright objects in principle. And the interesting thing is the periodicity pattern is completely changed. You still see a peak, and you see visibly the orbital period. These are, by the way, over 25 orbits from some random segment of the equilibrium state of the steady state behavior stage of the simulation. These are 25 black hole binary orbits. And you see by eye there's periodicity on the orbital timescale, but the more visible periodicity is on a longer timescale, which is why I spent so much time emphasizing about this lump. So the fact that this lump forms modulates the accretion on a longer timescale, which is the timescale of the orbit out here. So that's, let's say, 5-6 times longer than the orbital time of the binary. So if you plot a periodogram, you see both of those, and there are some harmonics. But the largest...
Can I ask a question about this?
Yeah.
Is this your green curves? Is that accretion rate onto the black hole, or just accretion onto the mini disk around the black hole?
No, this is accretion on the black hole.
But the mini disk, doesn't it take diffusion time to get through the?
In fact, most of the material that hits the edge of the mini disk is not necessarily even accreted. It might have a slingshot and fly outward. But eventually, the mini disk does accrete inward, and that's due to combination of viscosity in the mini disk itself. But also, you can actually see, if you watch the movie again, these mini disks actually have some resolved structures. It's not so clear in this movie, but they have resolved non-axisymmetric structures, which help gas going into the sink. And the sink, we just remove mass at the viscous rate in this inner region. So this is actually the accretion rate at which we remove gas.
I see. So the accretion viscous rate is 9 point. Okay.
Yeah.
Okay, thanks.
Okay. Well, I just have this reference here to those of you who know OJ287. It's kind of intriguing that OJ287 is a blazar, which is got a 12-year periodicity. This is just a comment for those of you who knows this object. It has pairs of outbursts every 12 years. And I just find it interesting that there are pairs of outbursts in this simulation, because the two black holes are slightly out of phase in the maxima of these longer periods. Okay, so I would say this is observational binary signature number 1, periodicity, which is either at the binary orbital period and clearer or somewhat more noisy period, which comes in pairs. One is at the longer period of the inner rim of the cavity and the orbital period. So another signature of binary as opposed to single quasar is the spectrum. And that's actually a very, very sort of obvious point, which is unlike for a usual accretion disk with one black hole where the only source of heating of the gas is viscous heating. Here we have another source of heating, which is the shocks. And ultimately the energy source for that is the binary's orbital binding energy, because the binary is sloshing the gas around and accelerating it and causing the shocks. These shocks heat the gas. I mean, again, you can go back to the picture. And this is surface density. I don't have here the temperature, but these shocked regions are hotter and radiate at higher. We assume it's all blackbody radiation. So they just emit at higher temperatures. And so there are 3 components. We can just sum up the surface emission throughout the whole circumbinary disk and compare it to a single black hole. So this is a decomposition where the red is the emission from the outer disk. This is scaled to some particular accretion rate. So these would be here soft X-rays. These would be very hard X-rays actually. This is the outer disk, which behaves the same as essentially a single black hole. And then it stops at the edge of the cavity. The mini disks are the hottest, so they emit this bump. And then rather than this kind of double bump feature, this is tempered by a bit that there are mildly less strongly shocked gas fluid elements in the cavity in the streams, and that's the green. So the total spectrum does look, this is the thermal emission, and it looks quite different from a Shakura-Sagnaïev disk. It extends to much harder energies and possibly have this dip feature. Third, I think, and third and last electromagnetic signature is afterglow. So now you can forget most of what I said about the prior to the merger phase. And this is just one slide of a whole set of other work, which any question? So as you know, after the black hole binary merges due to gravitational wave at the end, it suffers 2 effects. One is that it loses the rest mass of the remnant black hole is order 1% or few percent less than the sum of the component masses due to the burst of gravitational waves, and also suffers a recoil at the order of hundreds or thousands of kilometers per second due to the gravitational waves carrying off linear momentum, not just energy. And this is actually from a very old paper from 2008, where we took a black hole here, we put Keplerian test particles and Keplerian orbits, massless test particles, and then we say the black hole suddenly is kicked in this direction by, in this case, whatever, a few hundred kilometers per second. And there's a very interesting phenomena that happens, which is the trajectories of the near circular orbits change into ellipses due to this kick. And those are essentially epicyclic oscillations, which are at the local orbital frequency at each radius. So they're out of phase. So you set up a disk with a mass, either if you remove a few percent of mass or if you kick the black hole, you set up epicyclic oscillations at each radius, which are out of phase. And there are certain radii where they cause shell crossings, or in hydrodynamics, they cause shocks. So they look like this. this pattern. This is just this restricted three-body calculation. This here is a simulation version of this, which we did in 2010. This paper we actually, is more recent. We just had analytic formula for where these caustics are forming. But the hydro simulation is here, and you can see basically this is the density, and you see these concentric compressed rings of shocks which propagate outward, actually propagates at the kick velocity outward. This is another signature of a black hole merger, because it's a very unusual afterglow in the sense that these shocks get both brighter and stronger as a function of time, because the kick velocity is a larger and larger fractional perturbation to the orbital velocity as you go further out. So shocks tend to be stronger and higher velocities at further out. So this would be some kind of afterglow where if you monitor a LISA source afterwards, it's got an emission which is brightening and hardening over time. So this is the electromagnetic signatures. Now, we also said the impact of the gas disk on the orbit is another very important question. So about this, I have a couple of slides only, but essentially you can measure the effect of the black hole disk on the binary. And what this shows here on the left is an equal mass binary simulation, again, similar to what I just showed. The difference is that this is an orbit average surface density, so it looks much more coherent. So this is the surface density in the frame of the binary averaged over many orbits. On the right is the torque surface density. So this here is red means positive torque, meaning gas in front of this particular black hole is pulling it forward. So it's torquing the binary positively. So it's trying to expand its orbit. Gas behind the black hole is pulling it backwards. So it has negative torque. So, and actually, if you work on this topic at all, there's been a lot of excitement over the last 2 years, because 3 groups, including ours and one by Jim Stone and colleagues in Princeton, and the other one, Dong Lai and colleagues in Cornell, all found the conclusion that the impact on the orbit is mostly from just this pure gravitational torque of the gas. So direct accretion of mass and momentum is not as important. And B, the red, and that is dominated by this gas, which is very close to the black holes. So this is why this was actually very hard to resolve in simulations, and only recently was measured in this context. And all 3 groups found that this red, the torque from the gas ahead of the black hole is slightly larger than the torque from behind the black hole. So the net effect is that the gas disk, rather than helping the merger, is actually causing the binary to spiral outward. I think I'm going to skip all the details here, because this was a very interesting conclusion, and of course would be slightly, well, let's say, if you really want to use the gas disk to merge the black hole, if you have this surreptitious motive, then this is a bad news, that your disk is actually driving the binary apart. Luckily, in more recent work, we find that this is actually generically not the case. So this is a very recent paper by Chris Tiede, who's a student at NYU, and what this shows here is the same plot that I showed before. So this upper middle panel is for an equal mass binary. This is the surface density averaged over many orbits. This is the torque density. This is just some contours of the surface density. And one thing I did not yet say is that all these simulations tend to be, for numerical reasons, simulating disks whose Mach number is 10. or aspect ratio of 0.1. So these are two-dimensional simulations, and the Mach number, I mean the orbital velocity of the binary compared to the sound speed in the disk. And that's actually much warmer than typically you expect in an AGN at separations of hundreds or thousands of Schwarzschild radii. And so in this paper, we simulated cooler disk with higher Mach numbers or thinner aspect ratios. And these are just two examples where we just reduced the canonical number used in all previous papers by a factor of 3. And it does look quite similar, but if you look a little more closely, you can see that the gas density here, this is this color scale for gas density. So yellow is high, black is low. So if you look out here, you can see that making the disk cooler resulted in increased density around the binary. And in the torque density, you can see that more stuff has built up in these regions, which are essentially the cavity wall and inside the cavity wall. And we found that this increase in density is larger than the increase in density of the mini disks. And as a result, the dominant torque is actually no longer from this mini disk, but rather from these larger regions. And also the green stuff here, which is driving the binary to out spiral, is no longer dominant over the purple, which you see the color bar here. Purple is negative, green is positive. So this quadrant, which is removing angular momentum from the binary, now wins. So this is, again, if your goal is to merge black holes with gas disks, this is good news because it says the more typical situation of a thinner disk would be that it actually promotes the merger. And the typical timescales for this, if you scale this to a near Eddington accretion rate, I mean, it's related to the viscous time at the end, but it's of order millions of years. So this could be actually quite rapid, or tens of millions of years. And just another point is that, in fact, we have two other very recent papers where we changed other things. So it turns out the out spiral in the canonical case of an equal mass binary on circular orbit with a Mach 10 disk changes to in spiral if you change any of these assumptions, pretty much. So if you make the disk cooler, out spiral changes to in spiral. If you make the binary eccentric, even just a little bit larger than 0.1, it will start to in spiral instead of out spiraling. And if you make the masses unequal, also the sign of the torque changes, although here you have to make it quite unequal. This plot just shows that the total torque, this is A dot over M dot. So you can think of this as the shrinkage in the semi-major axis for every unit mass you accrete as a function of Mach number. And here it's positive, and as you increase the Mach number, it's negative. And you can also see that the total torque is dominated by gravity rather than accretion, which is very small, and just shown here.
A question?
Yeah.
So if you want the disk to absorb the angular momentum of the binary, I guess its mass doesn't have to be equal to the mass of the binary, but it can't be much smaller, right? Because
I think the local disk mass can be much smaller. It just takes longer. It will slow things down.
Well, of course, the issue is what's the Q of your disk?
What's the
Q, the tomb ring.
So all this I'm talking about, there's no self-gravity.
Well, no, I understand, but it's just that if the mass of the disk were to approach the mass of the binary and it were to have an aspect ratio less than 0.025, then it sounds like it would be gravitationally unstable.
You're right, but at any given time you don't need. So I think a better way to, I think the better way to phrase this is, yeah, if you wanted to affect the binary in a single orbit, you should have comparable mass around it. But if you're willing to affect the orbit over 100,000 orbits, then you just want to M dot to be large enough that you deliver that much gas and interact with your own mass in 100,000 orbits. All right, so at any given time, local disk mass can be quite small compared to the black holes, as long as the if the accretion rate is large enough and you wait long enough.
So this is approaching a substantial fraction of the saltpeter time then.
Yes, correct. So 10 million years would be
Yeah.
some substantial fraction of the.
Yeah. Okay, thanks.
So I don't know. I guess let's see. I have 5 more minutes. Actually, just tell me when I should stop. But the last part of this theory part would be a simple point, which is, can you affect the gravitational waves? That was my 3rd bullet, and the general answer is that this is more interesting for unequal mass binaries because the gravitational waves are weaker, and the impact of the gas on a companion that's low mass is larger. So we looked at in a couple of papers by my former student Andrea Derdzinski. What we did was same kind of simulation that I just described, but 2 differences. Difference 1 is that the companion is small. So here the mass ratio is 10⁻3. So this is academic exercise or a 100 solar mass black hole falling on a 10 to the 5 solar mass black hole. That would be a LISA source. The other difference is that the orbit of the black hole here is pre-specified. It's basically almost entirely determined by gravitational wave emission. So unlike the previous simulations where the orbit was set to be circular, here it's set to be an in-spiral due to gravitational waves. And this just shows the flow pattern around the perturber. This is very canonical. You've seen lots of these in exoplanet or planet formation simulations. This is basically Jupiter. Again, the only difference is that here Jupiter is migrating inward due to external forces, gravitational waves. But the flow pattern is quite similar. You establish this gas mini disk around it with these streamers, and we can again measure the torques. And the upshot is the following. So we do this simulation, measure the torque, and just for calibrating your mind, so this is the LISA signal to noise curve. This is 1 millihertz over here, and these would be 5-year observation periods for 10 to the 6 solar mass binary with a 10 to the 3 solar mass companion. These are 5-year LISA windows, and our simulation corresponds to this region here, which corresponds to something like near 10 to 5 Schwarzschild radii before the merger. So these low mass ratio, extreme mass ratio sources, they chirp very slowly. So that you can see they spend a long time in the LISA band and they execute, let's say, order 100,000 orbits. And so the idea is that the gas torques are small, but they can cause tiny deviation in the waveform compared to vacuum waveform. And the bottom right here shows the torques. The green is the gravitational wave in spiral due to standard quadrupole emission, but here phrased as a torque, expressed as an effective gravitational wave torque. And this here is the gas torque, the red, and the blue is the accretion of momentum directly. And this is 10 to the 4 times. So what you see here is that the gas torques are approaching 10⁻4 of the gravitational wave torques here at 10 Schwarzschild radii, and then it's more like 10⁻5 closer to the merger when the gravitational waves are stronger. But so this is a 10⁻5 effect on the LISA signal, but because we have 10 to the 5 cycles, this can cause an additional order unity cycles, and that's actually detectable by LISA. And the precise distortions here will of course depend on mostly the density of the gas in the disk, which just scales this torque linearly. So we've concluded that LISA can detect these deviations if the disk has a surface density larger than a few hundred grams per centimeter squared, which is certainly within some of the disk models. this is at at these separations of 10 Schwarzschild radii. So I think I probably should simply stop here because it's 3:05. So I don't know. This went much more slowly than usual. I think I'm gonna skip the next two parts and put up conclusions. I mean, you're feel free to ask about this, but my main conclusion, if you want to take away from this particular part of the talk, is that black hole binaries should be common, produced in mergers of galaxies, and there's no reason to expect that they're dimmer than a single black hole. On the other hand, there are strong reasons to expect that their light curves are periodic with some patterns that depends on the mass ratio. And then I didn't get to say this, but there are candidates we've discovered, we and a couple of other groups have discovered in optical surveys. There's a table of about 150 periodic quasar candidates. And so the question is, are they really binaries or just noise or something else that causes periodicity? I had some ways to discuss how you distinguish that, but I will stop. And then I just won't comment now on the stellar mass black holes. Maybe next time. So yeah, thanks for listening in.
Zoltan, I have a quick question. I wanted to ask about the out spiral, which I know happens in massive star formation simulations as well. So just to clarify, the energy source for an out spiraling binary has to be accretion onto the objects, right? Because you're putting energy into the orbit and into the shocks. So obviously that energy has to be coming from bigger reservoir, which would be accretion onto the deep potential wells of the individual objects. Is that right?
I think so, yes.
Even though accretion's not an important source of torque, it's a source of at least the energy for that process.
I think that must be right. I mean, I think the other way I like to think of it, before we had out spiral, is we had in spiral, and then you can extract the binary's orbital energy to light up the gas and produce the shocks. But here clearly it has to be from the accretion. Cannot.
I don't see how your accretion onto the central black hole is written into the code. It's shown. Is it thermal energy or is it?
With the accretion, sorry, can you?
To follow up with Chris's question, where's the energy source for the out spiral? You think it comes from the accretion into the individual black holes?
No, I think it comes from the accretion disk. Normally, the gas loses its energy to viscous dissipation, right? Here you instead lose orbital, the gas which is coming in from the circumbinary disk has potential energy and kinetic energy, and that's diminished and goes into the shocks and the orbit of the binary through gravitational torques.
Per mass wise,
I don't mean the source of energy is.
Oh, sorry, I misunderstood. Yeah.
I don't mean it's actually the individual black hole eating the gas that's the source of energy. I mean it's the gas that's accreted.
But per mass wise, that's very inefficient, right? Because
I agree. I don't dispute that. Yeah.
Going back to the lifetime of this process, if it's really lasting a substantial fraction of the time that the black hole is a bright accretor, shouldn't you be seeing binarity as a very common feature of quasars?
So I think that's, yeah, I think that's actually a very good point. And it depends on, so I have a whole talk on that, but I think it depends on well, yes, if the quasar phase coincided with this gas-driven phase, I think it should be very common actually. So it could be that the quasars light up, or mostly we see them later when they're entering the gravitational wave-driven regime, where it's when they're in spiral faster. So, for example, some of the candidates are 10 to the 9 solar mass black hole candidates. They're borderline in this gravitational wave-driven regime, and they're expected to live for 100,000 years. And I think the other issue is the scaling. The scaling is a little unclear because the simulations effectively are much thicker than a usual disk. So I think another confusion or unclear part here is when you derive this time scale, it's just you run a simulation which effectively has an accretion rate. One way to think, so it's very thick, much thicker than an actual EGM disk. So one way to think about that is its accretion rate is, I don't know, 10 to the 3 or 4 times Eddington. And then we just scale it by hand down to what it would be like for near Eddington. And maybe that scaling is not that obvious, that it works as expected analytically.
Thanks.
But yeah, I don't think I have a much more clear answer to that. And of course, maybe many quasars have nothing to do with these mergers, or they lit up before or after the merger.
Okay, are there any more questions?
Maybe just quickly, could you say something about the thermodynamics of the disks? You said there's a cooling imposed. Is that just a cooling prescription, or is this some type of radiative transfer with?
No, this is the simplest thing. We assume we measure the shock heating and the viscous dissipation. So that goes into increasing the temperature basically. And then we just assume an optical depth on the disk, and the temperature on the surface is, tau to the quarter times the midplane temperature, and then it radiates black body. So this effect, there's implicit radiative transfer through an optically thick vertical transfer.
Do you think any of the results would change if it were done differently?
So I think a lot of this result can change from radiation. This particular thing, we did check that in all our simulations that the disk optical depth does remain large, and that the disk does remain geometrically thin. So it's never heated so much that it should be H/R larger than 0.2. But more generally, these simulations don't have any radiation from the black holes, from the accretion. There's no photons, so the photons could definitely change the geometry. Can be dynamically important by changing the gas distribution. I think especially susceptible to that is what I described here. If all the torques are caused by the tiny asymmetry on the mini disk around the hole, and if you're relying on that conclusion, I think that's particularly prone to 2D versus 3D radiation, jets, magnetic fields, I think. So this is just the first step. A lot more work should be done. I'm just emphasizing that it's a tiny asymmetry that causes the net effect.
Okay, any more questions?
I'm curious whether at the end of your 10,000 orbits, is it possible that did the binary become more eccentric, or you kept them fixed?
So we didn't run a live binary. So this is the only paper. So this paper, which actually I think was last week on SMBH, we ran a series of simulations with fixed eccentricities. And the main conclusion of this paper is that I should have brought them plot. I think I don't have the plot. Let's see if I have the plot. Well, let me. Sorry, I don't have that plot here. The conclusion is that there's a stable eccentricity of 0.45. So if you take eccentric binaries which have eccentricity below 0.45, eccentricity is going up due to the disk. And if you take a more eccentric one, it's going down. And so, this implies there's a stable value of 0.45, and presumably after enough orbits, these binaries are driven to this value of 0.45.
Okay, it's a magic number.
Magic number, yeah.
I mean, we see a lot of stellar binaries with fairly eccentric orbits.
Actually, yeah. So this is a new paper, and I think it's actually very exciting because it's again scaled to m dot. So you reach the 0.45 after you accrete some significant fraction of the mass. But so therefore you expect some distribution over time. So you get to 0.45 after you accreted, I forget the ratio, 10% of your mass or something like that. So if you start with some distribution of eccentricities initially, it starts to converge to this 0.45, but doesn't necessarily get there. So it implies an eccentricity distribution. And we compare this to a distribution of post-AGB stellar. So stellar binaries of post-AGB stars, which are known to have these circumbinary disks, and it looked very, very similar actually.
Well, you might want to look at binary massive stars, young massive stars, which accrete all their mass. So you don't have to worry about only accreting part of it.
I see. So yeah, it would be useful to, because yeah, I was surprised in stellar literature. Of course, there's so many analogies, so I don't any references are appreciated. I'm not nearly as familiar with the stellar literature as the black hole literature, even though I should be, because
It's the same dynamics.
Because a lot of the simulations are very similar. I should advertise actually on this point that to fix this problem, we have just got approved a KITP workshop for spring 2022. The entire purpose of that workshop will be to compare stellar and black hole binaries. And you'll of course be great to have stellar experts as well.
Fingers crossed for spring 2022.
So yeah, put it on your calendar. It's it's six. Some March is included, but I'm probably we'll probably receive an email soon anyway about it. It's February, March of 2022. So lucky. I mean, hopefully after pandemic when it doesn't have to be on Zoom. So that was organized by Dan Dorazio and Caitlin Crater and myself, and Yanfei Jiang from Flatiron Institute, 4 of us.
I think we've gone over time, so let's thank Zoltan again for this wonderful talk.
So thanks for inviting me.
And I think if you want to